Have you ever wondered why cryptography is such a critical aspect of cybersecurity? Cryptography, at its core, is about safeguarding information by transforming it into an unreadable format known as encryption. Imagine sending a letter through a crowded room. Without encryption, it's like sending your message on a postcard for all to read. But with encryption, it's like sealing your message in an envelope, invisible to prying eyes. Cryptography is the guardian of our digital world. It ensures the privacy of our data, keeping our personal information, financial transactions, and confidential communications secure. It maintains the integrity of data, ensuring that it hasn't been tampered with during transmission, and it verifies authenticity, confirming the identity of the communicating parties. Cryptography is not just about code and algorithms, it's about protection, privacy, and trust in the digital age. It's a crucial part of cybersecurity. Now that we understand why cryptography is a vital tool in cybersecurity, let's dive into the different types of cryptography algorithms and how they work. Imagine having a secret language that only you and your friend understand. That's essentially how symmetric cryptography works. Picture this. You're sending a secret message to your friend, and you both have a special key. This key is used to scramble the message into what seems like a random string of characters. To anyone else, it's gibberish, but to your friend, it's a message because they have the same key to unscramble it. That's the essence of symmetric cryptography, a single key for both encryption and decryption. Now, you might recognize some popular examples of this concept. There's the Data Encryption Standard, or DES, which was once the go-to method for secure communication. Then we have triple DS, or 3DS, which applies the DS method 3 times for added security. And of course, we can't forget the Advanced Encryption Standard, or AES, and Blowfish, which are widely used today. The main advantage of symmetric cryptography is its speed and efficiency. Because we're using the same key to encrypt and decrypt, it's faster than other methods. However, it does have a significant drawback, the key distribution problem. How do you securely get the key to the person you're communicating with without it falling into the wrong hands? While symmetric cryptography has its advantages, it's not the only type of cryptography out there. Picture a scenario where you have a lock that can be locked with one key, but needs a different one to unlock it. This is the essence of asymmetric cryptography. Now let's take a deep dive into the world of asymmetric cryptography, a fascinating realm where 2 different keys play a crucial role. Yes, you heard it right, 2 keys, one public and one private. These keys are a pair, each unique and connected in a special way. The public key, as the name suggests, is shared openly, while the private key remains a secret, known only to its owner. In this dance of codes, a message encrypted with the public key can only be decrypted by the corresponding private key. This ensures that even if someone intercepts the message, they can't make sense of it without the private key. Pretty nifty, right? 2 of the most famous examples of asymmetric cryptography are RSA and ECC, short for Rivest-Shamir-Edelman and elliptic curve cryptography, respectively. RSA, the old guard of the field, relies on the fact that it's extremely hard to factor large prime numbers, while ECC, the newer player, uses the mathematics of elliptic curves to provide the same security with shorter keys. The main advantage of asymmetric cryptography is its enhanced security. Even if a hacker intercepts the public key and the encrypted message, they can't decrypt the message without the private key. This makes it an excellent tool for secure communication on the internet. However, every rose has its thorns, and the thorn in the side of asymmetric cryptography is its speed. It's slower than its counterpart, symmetric cryptography, due to the complex mathematical operations involved. But in the grand scheme of things, this trade-off is often worth it for the added layer of security. Asymmetric cryptography provides an extra layer of security, but there's another type of cryptography that combines the best of both worlds. Tune in to our next scene to find out more about it. What if you could combine the speed of symmetric cryptography with the security of asymmetric cryptography? Welcome to hybrid cryptography. Imagine a world where you could enjoy the best of both worlds. That's precisely what hybrid cryptography does. It merges the speed of symmetric cryptography with the security of asymmetric cryptography, providing a robust and efficient solution. So, how does it work? Hybrid cryptography operates by using asymmetric cryptography for key exchange and symmetric cryptography for data transfer. It's like having a secure mailbox where only you and a trusted friend have the keys. You use your unique keys, thanks to asymmetric cryptography, to securely exchange a common key. Once this common key is securely exchanged, you both use it to lock and unlock the mailbox, akin to symmetric cryptography, enabling fast and secure communication. A classic example of hybrid cryptography is LTLS, the security protocols that protect your data as it travels across the internet. When you see that little lock icon in your browser's address bar, that's SSL-TLS at work using hybrid cryptography to secure your data. The beauty of hybrid cryptography lies in its ability to provide both speed and security. It efficiently combines the strengths of symmetric and asymmetric cryptography, harnessing the power of both to create a secure and efficient communication channel. Hybrid cryptography efficiently harnesses the strengths of both symmetric and asymmetric cryptography. We've taken a deep dive into the world of cryptography algorithms. Let's recap what we've learned. We started with symmetric cryptography, the oldest method, where the same key is used for encryption and decryption. It's fast and efficient, but sharing the key securely can be a challenge. Next, we ventured into asymmetric cryptography, where two keys are involved, a public key for encryption and a private key for decryption. The beauty of this method lies in its secure key exchange, but it requires more computational resources. Then we explored hybrid cryptography, a blend of the previous two. It combines the speed of symmetric cryptography and the security of asymmetric cryptography, providing an optimal solution for many applications. Each of these methods has its unique features, advantages, and disadvantages, and they are all vital tools in the cybersecurity toolbox. Understanding these cryptography algorithms gives us a better grasp of how cybersecurity works, protecting our data and ensuring our privacy in the digital world.